Hello everyone, today I'll be explaining my solutions to biweekly contest 86 and so far this is by best contest and let's start with the first problem. So first problem asks us to find the subarrays with equal sum, specifically subarrays of length 2, and subarrays of length 2 is just two consecutive values, so we start from the first index and we keep on storing the sum in a map or an array, and then we can basically a counter. And then whenever we again traverse the map, and if the frequency of some sum is greater than or equal to 2, we can return true or else we can return false. It's just basic brute force works here, and the contest is still running, I think. Yeah, so that's what I have done. I have created a map of long because maybe overflow can occur, so I didn't want to take the risk. And from 0 to n minus 1, because you need to access the I plus 1th index just to avoid out of bounds error, and you put this in a map and increment the frequency and iterate over the map, and if the frequency of any sum is greater than or equal to 2, return true, else you can return false in other cases, right? Next problem is strictly palindromic number. So you're given an integer n, and it is strictly palindromic if for every base from 2 to n minus 2, both inclusive, the string representation of the integer n in base b is palindromic. So, and we need to return true again if that is palindromic or not, strictly palindromic or not. And the constraints are n less than or equal to 10 power 5. So that means the maximum length of the, if we convert the number into a string, the maximum length won't cross 6. So in that case, we can try all possible bases from 2 to n minus 2 and check if that conversion from base 10 to base b is a palindromic string or not, right? So for that C++ already provides in two string function. C++ already has this conversion directly, but I wrote my own implementation for that string decimal 2. So yeah, first we need a function to check if it's palindrome or not, and then we start from base 2 and iterate till base n minus 2, and if the current base string is not a palindrome, you return false, else you return true. So the way in which I check that is, I have a single digit function which just returns the it takes each integer and it returns a character. So if it's lesser than n, lesser than 10, you just add a 0 and return it, or else whatever it is, you can decrease the value 10 and you can add a and return the sum. So you can understand this function using hexadecimal base, it will be easy. And the main function is this. So if the decimal value is 0, we can directly return 0, or else while the value is positive, this is same as like converting it to binary. How we do it, we add the remainder, which is decimal modulo base, to which is the current remainder, and then we keep on dividing the number by the base, and then we push the remainder to the remainder stack, and then the string which is formed later is just, so we'll push the single digit representation to the stack, not the direct remainder. And yeah, the answer is any base this string, and while the stack is not empty, we'll just keep on adding top of the stack to the answer, and then we can pop the stack. Yeah, so we are using stack just to reduce the we can also use vector here, it's not an issue. If we use vector, we need to make a reverse call here, just to avoid that we are using stack here. So that is it for the second problem. And let's move on to the third problem. So the third problem is maximum rows covered by columns. So we are given a m cross n binary matrix and integer calls, which denotes the number of columns you need to choose. So I'll represent this as n cross m matrix, and we are already given the total number of columns we should choose. So we have to choose any combination of let's call it as x columns, and such that it satisfies a condition. That condition is, a row is covered by a set of columns, that is the chosen columns, whatever set of columns we chose. If each cell in the row that has a value of 1 also lies in one of the columns of the chosen set. So that is basically, in this case, we have to choose two columns. So in among different combinations, like we have four combinations. In one of the combination is choosing the first and last column. In that case, we can see here these rows have one in this row, except this row, every other row which has one either belongs to the first column, that is the zeroth column, or the last column. So that is the case here. So the reason why we are not selecting this row is because we have a 1 in the middle which doesn't belong to the set of columns we have chosen. So that is the case they are giving here. And it's the way in which we generate all possible combinations for a given number. Even if we are not given this and asked to find the maximum number of rows, you can call that as a follow problem maybe. In that case, what we can do is we can use bit masking and generate all the subsets, basically all combinations, and then we take the maximum among all combinations. Then in this case, since we are already given columns, we can again do bit masking, but only consider those subsets which has subsets of length columns. So that is the only thing we have to do here. So the algorithm is just do bit masking, generate subsets, and consider only subsets of length columns, and for each considered subset, each valid subset, check this condition, that is, if there is a 1, it should belong to any one of the chosen columns, or you can have a 0 at the positions. It's not an issue. So you check that for each row. If any row satisfies the condition, you have a counter and increment the counter, and at the end take a maximum of all the counter variables. That's it. So the code is like this. As I said, n cross m, I'll consider it as n cross m, and we iterate through all subsets of so all the 2 power m subsets, and we can do this because m is just 12, so 2 power 12 is 4000 or something, so we can do that. And for each subset, we have this columns boolean vector which just says whether we have whether this particular column is in our subset or not, and we can check that using if the mask, and if the cth bit is set in mask, that means the column we are choosing the cth column. So we set that as true, and we need to count the total number of chosen columns in the subset. So for that, we can directly either we can have a for loop and make a counter, or we can just directly find the sum of the boolean array, which will give us the total number of chosen columns for the current subset. Basically, this is the size of the current subset, right? So if that is not equal to so I have renamed this columns as required here. If that is not equal to required, just continue and check the remaining subsets. If that is the case, have a counter variable and go through all the rows, and for each row have a boolean flag variable, and for each cell, this is the case, either the cell should contain a 0, or if the cell doesn't contain 0, that means it has 1. If it has 1s, that particular column should be there in our chosen subset. So that is the condition. So this is like OK equals OK and this case. So this will become false whenever any one of this case fails, right? Because we are doing an AND operation. So if even any one case fails, any one false occurs, the whole flag variable will become false. So we'll just add OK to the counter variable. So only if it's true, we'll add 1, and then we'll take the maximum of the counter and return the answer. So that is the third problem. And the fourth problem, so this is an interesting problem. So in the fourth problem, we are given 2 arrays actually, and it's charge times and running costs, and both of length n. The ith robot costs charge times of I units to charge, and running costs of I units to run. You are also given an integer budget, and the total cost of running k chosen robots is equal to maximum of charge times plus k times the sum of the running costs of those k chosen robots. and where maximum of charge times is the largest charge among the k chosen robots, and sum is just the sum of running costs of the chosen robots, right? And we need to return the maximum number of consecutive robots you can run such that the total cost does not exceed the budget. Okay, so this particular thing itself is a gives away that the problem requires some sort of binary search or something. So that is the first thing we have to note here. So this statement, we need to find something maximum or minimum or something such that some parameter doesn't exceed or doesn't cross some another value, another parameter. And we also have an array, and if you see this as a function, you need to maximize this function, right, such that you need to find the maximum value which is minimum, such that the maximum value which is less than or equal to budget, right? So that is let's say this function is just f of k gives the maximum of let me call this array as charges and this array as runs, and maximum of max of charges plus k times sum of runs. So this is a function and we need to maximize this function, right? And we need to find that value, maximize this value such that it is less than or equal to budget. So maximum less than or equal to budget. So this is somewhat resembling to a minimum, minimax or maxmin. So in all those cases we will be using a binary search only, right? So in all those cases we'll be using binary search only. And so the way in which we can prove here that we can use binary search is by going through this, by looking at this function, right? So we only care about the consecutive robots, right? So we can say that if we can let's say if we can find if there is a if there are 5 consecutive robots such that their function f of k let's say if f of 5 is lesser than or equal to budget, can we say that f of 4 is also f of 4 will also be less than or equal to budget by looking at this function, right? Because maximum of charges may or may not be the same, and k will be replaced with k minus 1, and sum will also get reduced, right? So it will always be less than or equal to, so what I'm saying is f of x will always be less than or equal to f of x plus 1. So because of that we can say that if f of 5 less than or equal to budget, f of 4 will also be less than or equal to budget. So this is the case. So for all x lesser than let's say y, if f of y is less than or equal to budget, f of x will also be less than or equal to budget. So this is the the monotonicity of this function f of x function. And since this function is monotonic, we can use binary search on this. So the objective of this function is our objective is to maximize this function f of k. So the way in which we can maximize this, we need two parameters here. The first is maximum of charges, and k we also need, and then we also need the sum of the chosen robots. So it's not like we have to choose some subset of robots, we have to choose a consecutive set of robots, right? So that means we have to if we have an let's say if we have an array of length 8 or something, and k is 4, we'll try out all possibilities, right? We'll try out first 4 values, the next 4 values, the next 4 values, the next 4 values, and so on till the LWA. And we'll check if any one of these subarrays, if the f of x value of any one of this subarray, that is this value, is less than or equal to budget or not. If that's the case, that this is true, right? That is like f of x less than or equal to budget is true. If this is possible, f of x minus 1, it will also be less than or equal to budget, so there's no point in checking all the values which are lesser than x, right? So we'll move on to the right, that is we'll set the binary, the high pointer in binary search to mid plus 1, and we'll check, we'll do the same, we'll try to maximize the f of x on the right side, we'll check if it's possible or not. So as soon as this case is true, we'll update our answer to be x. So x is just the length of the array, so that will be this function f of k f of x. So x is the length of the subarray we are considering. So you can see here we are using sliding window here, and in each binary search we will be sliding the window of k consecutive elements, and we will be checking if it satisfies the condition or not, if f of x is less than or equal to budget or not, right? So that's one thing. And next, let me write the function here. So f of k is equal to maximum of charges plus k times sum of runs, right? So let's look at what these things are separately, right? So k is already given in binary search, we'll always pass k to it, and we don't know which consecutive, let's take the same example of having subarray, having an array of length 8, and let's say k is 4, right? So we'll choose first 4, next 4, next 4, and the next 4, right? And we want, for each of these smaller window, we need to find the maximum of that window in the charges array, and the sum of the windows in the runs array, right? So for each window we need to find the sum of runs from L to R, where L and R represents the window, starting and ending points of window. We need this, and we also need maximum of charges of L to R, right? So how to do this? So this is this particular thing, we need both of these things in lesser than order of n time, right? Because already we'll be doing a binary search of log n term, and in each binary search we'll be doing a sliding window, so into n, and we can't have again n here, right? That will be order of n square, and that doesn't satisfy the constraints, right? Because you can see the constraints are already 10 power 4, so n square log n won't work here. So we have to do that in less than order of n time, right? So the way in which we can do that for computing the sum of some subarray in less than linear time is using prefix sum. So using prefix sum, we can find this sum in constant time, and if we already build the prefix sum array in the main function and pass it to the binary search in each iteration, we can compute this in order of one time. And the way in which we find the maximum of charges, like maximum of a subarray, of a static subarray, this subarray runs, the charges array doesn't change, right? So it's a static array, and we need to find a maximum in static array. So if it's a dynamic array, we can use segment tree and find the maximum value for any subarray, but even here we can do that will add one more logarithm complexity, or else, so this is segment tree plus sliding window plus binary search plus prefix sum, this approach. Or else what we can do, since this is a static array, we can make use of that fact, and we can use the same sliding window plus binary search plus prefix sum, and the time complexity will be log n for binary search, n for sliding window, and we can use a data structure called a sparse table, which will give us constant time, which will help us do constant time queries, but close to constant time queries, and order of n log n space, and order of n log n space, and n log n build time as well. So that is just constant time, right? So this is time complexity of the binary search, sliding window. Prefix sum is also constant, and this is from sparse table, plus building time of sparse table is again log n. So this is just order of n log n solution using sparse table, sliding window, binary search, and prefix sum. So sparse table will just tell us what is the maximum value in this range L to R, and prefix sum will tell us what's the sum of the array runs in this range. That's it. So we'll plug in all these values in the formula, compute f of k, and check if it's less than or equal to budget or not. If that's the case, return true. If any one of this is fine. If any one of this is fine, or else return false if no subarray satisfies the condition, right? And then we'll go to the left side of the search space and keep on exploring there, and finally we'll have an answer, optimal answer, right? So that is the approach here. It's a really interesting problem, and it uses a lot of techniques like sliding window, binary search, prefix sum, and sparse table. So usually these things are very common used together, binary search, prefix sum, and sliding window, but using sparse table is interesting here. So yeah, that is it. So I think this is the most optimal solution, because you are doing unless there is a linear time solution, I think this is the most optimal solution, because you are doing static range max queries in constant time. So yeah, I think this is the n log n is the most optimal solution. Not sure, but yeah, so that passes. Let me explain the code as well. So this is my sparse table template. I already have my template. So the build time here, as you can see, is n log n, and space is also n log n. Yeah, and then yeah, the queries are just, you can just see here, it's just constant time queries. So these built-in count leading zeros, these bitwise operations are considered very fast, so it's constant time only. And then so one more thing in this problem is we should take care of overflow. So for that purpose, I'm using long everywhere. And then yeah, so I am declaring the sparse table and the prefix sum array as a member variable in the class, so that I don't have to pass it every time to the check function in the binary search. Yeah, so initially we take the prefix sum and store it in the PA array, prefix sum of runs array, and then we need to create a sparse table of this charges array, and the combine function is just maximum function, so max of x comma y, and we just binary search over the possible answer. So worst possible case is no subarray satisfying anything, so that is 0. Initially I'm assuming it's 0, and I'm starting the binary search from 1, because in some problems I used to get runtime errors because of this. If we use 0 here, it will go here and it will try to check for 0 length subarrays, which doesn't exist in the array. So in order to take care of that case, I'm starting from 1 and going on till n. So n is the best possible case, and just do binary search and check in each iteration, check if this is possible, check if any for any subarray f of k is less than or equal to budget. That is this. So that's what the check function returns. So one more thing to note here is we need to pass everything by reference, or else again TLE will get. And yeah, so the first subarray from 0 to k, that is 0 to k minus 1 index, we need to find the f of k. So this current is just f of k, and 0 to k minus 1 we'll get the maximum value, and k is there, and then the sum, which is prefix sum pa of k minus 1, the first k values. And if that is less than or equal to budget, return true, or else check other windows. So all the other windows will be represented using 2 pointers, which is I and I minus k. I minus k is I minus k plus 1 actually. Yeah, I minus k is just one index before the starting point of the window. So L is I minus k plus 1 and R is I. So get the maximum in this range, get the sum in this range. So this is the one index before, I minus k is one index before the starting point of the window. And if f of k is less than or equal to budget, return true. If nothing is possible, return false. And yeah, that is it. All the problems are solved. Thanks.